We'll start motivating leader-based sequence Paxos. We will introduce a leader among the set of proposers. Any proposed command is forwarded to the leader. As we will see in the next unit, this allows correctness-preserving transformations of the vanilla sequence Paxos algorithm into an algorithm where proposals can be pipelined asynchronously. And most proposals will take one round trip with minimal contention under good network conditions. However, we will need a special leader election abstraction and the corresponding algorithm. This we will cover next. The current algorithm for vanilla sequence Paxos has a number of problems. The algorithm, as presented, satisfies all safety properties, but may not make progress. There is a number of problems we have. So a proposer can run only one proposal until decide before taking the next proposal. So there are no pipelining of proposals. Because we have multiple proposals, this may lead to a deadlock, as we know that if there are multiple proposals, one can run over the other. The first one can do a prepare phase, and then before going to the accept phase, the second one does a prepare phase and aborts the first one, and it goes on. We have 2 round trip for each sequence chosen, or every sequence extended and chosen. And the entire sequences are sent back and forth. If you remember, VP, the sequence at the proposer, VA, the sequence at the acceptor, and VD, the sequence at the learner, are mostly redundant. And we are going to solve this problem by introducing leader-based version of this algorithm. So we'll elect a leader among all processes. The election is eventually accurate, so multiple leaders may coexist, but we eventually will have a leader to agree upon. What are the assumptions we have? So we assume an eventual leader election abstraction with a ballot number. We call this a ballot-based leader election. So a leader, when he becomes a leader, he will send an indication event saying that I am the leader and this is my ballot number. Ballot-based leader election satisfies completeness and eventual accuracy. By completeness, in this case, if you remember, so eventually every correct process will trust one correct process as a leader. And eventual accuracy means that eventually there will be an agreement on the leader. We also add a new requirement, which is basically the ballots that are emitted will be monotonically unique ballot numbers, and they are monotonically increasing. So a leader-based sequence Paxos will be optimized for the case when a single proposer runs for a longer period of time as a leader. Thus, it will not be aborted for a while, and it always guarantees safety even if it is aborted. So let us look to the desirable features of a ballot-based leader election algorithm. So a ballot leader election elects a leader L with higher ballot number N than all previous leaders L prime. So this is the basic idea. You become a leader. If you are a leader, you emit a ballot number or a round number, which you inform the other followers. And this number is higher than the number of previous leaders. Just to say it exactly, if a process P elects a leader, Ln, so this is the indication event at process P. Then, for all previously elected leaders at P, it is guaranteed that N prime is less than N. That's it. And all ballot numbers are unique. So it means every process sees a leader. He could be also a leader, but he sees a leader with a ballot number 5, then he sees a leader with a ballot number 6 or 8, and so on. But these ballots are monotonically increasing, and it is unique per leader. So here is a time-space diagram where you can see the situation. We have 3 processes. So at process P1, he gets an indication event or an output event that says P3 is a leader with a ballot number N. And that happens also at P2 and at P3. Now P3 crashes. So here is a situation where P1 gets an indication that another process is elected. So P1 gets an indication that another process is elected. In this case, it is process P1 with a ballot number N2. So N2 has to be higher than N1 and is unique. So no other leader will come with this N2 again. Then he elects a leader which is N3, which is fine, but N3 must be higher than N2. And eventually, both again elect a leader with a ballot number N4, and here we have an agreement at this point. So you can see that leaders might overlap. So for example, here's a situation where in this period, until this period, where P2 thinks that P3 is a leader, while P1 thinks that P2 is a leader. So this is an example. So you can still have overlapping leaders. Eventually, they will elect the same leader. But most importantly, that when you elect a leader, it comes with a unique number that has not been selected before for another leader. And this is a requirement of Paxos. So now we have our current algorithm, which is the vanilla Paxos algorithm, has a number of problems. I'll just state it again. So the previous algorithm presented satisfies safety property, but as we said, a proposer can run only one proposal until it is decided before taking the next proposal. So there is no pipelining of proposals. Multiple proposals may lead to live locks, and 2 round trips are needed for each sequence extended. And there are other aspects. Sequence are sent forth and back, and also all these variables, the sequence at the proposer, at the acceptor, and as the decider, are all redundant. By just introducing a leader without doing so much changes in the algorithm, we will be able to pipeline proposals, and we will be able to avoid live locks and contention, and we will be able to execute most of the proposals on one round trip. Then we need some still modifications to address these 2 issues. So let us go now to think about the state of the different processes in our algorithm when we have a leader-based election. So we have a set of proposals, and among these proposals, one will be always elect the leader. So we still have a set of proposals. And any proposer will be either a leader or a follower. So this is the state of a leader, and this is the state of a follower. Initially, all proposals are followers until the first election round. One of them will become a leader, and the rest will be followers. Say a leader, on the other hand, within a leader state, it can be either in a prepare phase. You remember the Paxos algorithm has 2 phases. One is a prepare phase, and the next one is an accept phase. The prepare phase is just getting the authority to propose values, and it's getting it from having a set of acceptors that agree on him. So these 2 phases will be quite different. So therefore, a leader will be either in a prepare phase or an accept phase. And once some other leader is taking over, so the leader will move to become a follower.